Hi, I want to give you some background information about my talk, including some of the theory of electron transfer and non-adiabatic dynamics. So first, let's talk about just the phenomenology. As I mentioned in my talk, imagine a system where you simply have a water and two irons. And imagine the system as a +6 charge. Now, it's pretty clear from this description that you'll have to have an iron +3 on the left and an iron +3 on the right. That's pretty clear by symmetry. Now, if you include one more electron, then the final charge should be +5. And by symmetry, therefore, you have to have a charge of 2.5 on both the left and the right if the water is symmetrically oriented between left and right. How could it possibly be any different? However, if that molecule rotates to the right, that water molecule, then it's pretty clear that you've broken symmetry. And now, in principle, you should have lone pairs on this oxygen, which are looking for a positive charge. And that means that the ground state will have to be a +3 on the right for the iron here and a +2 on the left. And vice versa, if the water shifts this way, then it's clear that you must have lone pairs now on this side of the oxygen, and it'll be an iron +3 on this side and an iron +2 on this side because the electrons over here are going to want to talk to this plus charge. That gives us the following potential energy surface, which looks like follows. If we look at the ground state energy as a function of the twisting angle of this water molecule, then it becomes clear if the water molecule is not twisted, it must be 2.5 on the left and 2.5 on the right. However, if the molecule is twisted, then it must be, as we said before, that if the molecule is twisted this way, the lone pairs are here, it's a +3 and a +2. And if it twists the other way, it's a +3 on this side and a +2 on this side. Now, of course, there can be multiple electronic states, and that's going to come out in a second, because the big question that you ask dynamically is, if a water turns slowly, is there an electron transfer? And the answer is yes, of course, that has to be. You're moving along this potential energy surface. That's the whole idea of a potential energy surface, that as the water spins, you move along it. And it's clear that if the water spins slowly, then the electron is going to move from the left to the right iron. But if the water were to spin fast, there would be no such time. There'd be no such time because think about it. It does take some time for any electron to move. It takes time for anything to happen. So if the water spins fast enough, there's just no time. So the electron must stay on the left. All of that tells you that the basic essence of what is called Marcus theory today, that you actually have two surfaces, a ground state and an excited state. And the ground state, we know if the water is in this configuration, the water is pointed, in this way with the lone pairs on the right, really the ground state should be +3 and +2. But that means the excited state must be over here, a +3 on the left and a +2 on the right. The electrons in the irons not matching the electrons in the water. It's a much higher energy configuration. In the middle, it'd be 2.5, 2.5, and on the right-hand side, it'd be different. And the idea that we have in Marcus theory is that, therefore, if the water spins slowly, you move along the lower path. But if the water spins fast, you jump up and around and you break surfaces. This is called non-adiabatic motion. The idea is that the nuclei no longer move on one surface. And what I want to do is explain to you, in the most simple terms possible, how this arises quantum mechanically. It's not magic. It's all in the Schrodinger equation if you think about it for long enough. So how does this work? What's the theory of this motion? And the idea is it's simply electronic structure combined with dynamics. Okay, so understand this. Let's just go back to the essence of the electronic structure problem. In electronic structure, we know always that the Hamiltonian is a combination of kinetic energy and potential energy. If the electronic structure problem, we know what this means. The potential energy wants to localize an electron around the nuclei, and the kinetic energy wants the electrons to be as delocalized as possible. And it's the competition between these two forces that gives us molecular structure and electronic structure theory. The fact that T and V don't commute, but the sum of T plus V will be something somewhat localized and somewhat delocalized. That's the whole notion of how you get molecular orbitals. And in fact, of course, that's what most of us spend all of our time doing. We spend hours upon hours solving the electronic structure problem for molecules if you're a quantum chemist, for materials if you're a solid state physicist or a materials scientist. Okay. And in fact, I use oftentimes the QChem platform. And the point is that really the nuclei have very little to do with the electronic structure problem. They give you the potential that you have to work with, but all the different levels of theory you use, Hartree-Fock, TDDFT, MP2, they really have very little to do with the nuclear motion. Nuclei are frozen, right? The nuclear mass isn't even put into these calculations in general. Okay, but we're used to the idea of T plus V. So really, electron transfer comes about because that's not the full Schrodinger equation that you have. What we've talked about so far was the electronic Schrodinger equation, but the full Schrodinger equation is the nuclear plus electronic Schrodinger equation. There, for such a Hamiltonian, you have not just the kinetic energy of the electrons and the potential of the electrons, you have the kinetic energy of the nuclei plus the kinetic energy of the electrons plus the potential energy of the nuclei and the potential energy of the electrons, the repulsion, and then the attraction between nuclei and electrons. And electron transfer comes in because of the competition between all these different forces. What does that mean exactly? Now, by the way, in the nomenclature here, and not just in my talk, but in every book you're going to see, little r is always the electronic coordinate, and capital R is always the nuclear coordinate. And more often than not, you will see this Hamiltonian as such, this total Hamiltonian rewritten as the nuclear kinetic energy, plus the so-called electronic Hamiltonian, which is everything else over here. Okay? Now, within electronic structure theory, what we do is we freeze the nuclei, which means that we forget about the nuclear motion and we just diagonalize this part, the so-called electronic Hamiltonian. And when we diagonalize that part, we end up generating electronic eigenfunctions and electronic eigenenergies, which depend parametrically on the nuclear position. These are adiabatic states, right, in the literature. These psi's are called adiabatic states, and this V eigenvalue is called the adiabatic energy, which is also the same thing as a potential energy. These are the potential energies that chemistry happens upon. These are the potential energies that you solve all the time to look for stable geometries of molecules and their associated electronic wave functions, molecular orbitals. Okay, now of course, as mentioned before, for the iron-iron example, but even more clear for the lithium fluoride example, these surfaces can cross. Why do they cross? Well, let's just take lithium fluoride as an example. It takes about 5 electron volts to pull an electron off of a lithium, and you get about 3 electron volts when you attach that electron to a fluoride. So in principle, there's no reason that you do not have a clear electronic motivation to form an ionic bond of lithium plus and fluoride minus. But of course you do, right? We know high school chemistry tells us that lithium fluoride is an ionic bond, lithium plus fluoride minus. So why does that happen? It happens because not only do you have to worry about the energy it takes to pull an electron off of lithium and the energy you get back by putting it on the fluoride, you also have the attraction of lithium plus and fluoride minus. And when they're close together, they're strongly attracted. That gives you an extra stabilization energy, which is why you have lithium plus and fluoride minus. But when you pull them apart, there's no stability there whatsoever. And then it becomes more stable to have lithium neutral and fluoride neutral, as opposed to lithium plus and fluoride minus. So this is a so-called avoided crossing or a curve crossing. At long distances, the ground state wants to be lithium fluoride neutral. But at short distances, it wants to be lithium plus fluoride minus. And in the middle there, that's where all the action is. And you can think of electron transfer as a simple question asking, if I had a lithium plus fluoride minus, and they were far apart and they were attracted to each other, when they come together, will an electron move and create lithium fluoride neutral, or will it stay lithium plus fluoride minus? It's a very simple question to ask. How do you solve it? Well, again, you have to consider the total Schrodinger equation, which is the Schrodinger equation of the nuclei plus the Schrodinger equation for the electrons. That's your total Schrodinger equation. And the Born-Oppenheimer treatment is usually the approximation, is usually the framework or the formalism that we make. The idea is that you diagonalize the electronic Hamiltonian, you generate eigenstates, and then, oh my God, is this, yeah, not such a great notation. Oftentimes people use not psi's, they use chi's. But in any event, you have a nuclear wave function on state J and an electronics wave function on state J. This is my total. And the total wave function is a function of the electronic position and the nuclear position. And when you then diagonalize this whole matrix, you have to solve this whole equation that the kinetic energy of the nuclei, right, plus the electronic Hamiltonian on this total wave function equals E times psi. Now, when you work that out, it's pretty easy to see you're going to have a problem here. Well, not a problem. You're going to have some rich physics because this psi total, right, depends on the nuclear wave packet and the electronic wave packet, and both of these depend on the nuclear position. So when this operator here, the kinetic energy operates on psi total, you're going to get derivatives from here and from here and from both, and that's exactly what you see here. This is what the Schrodinger equation looks like. It's this kinetic energy operator plus the potential energy operating on a nuclear wave packet, and then plus some other crap. And this is the other crap that hides all the details about how wave packets move between surfaces and how it is, let's say, that you actually get electron transfer. So in this case, what do you actually get here? If you were to look at this expression here, what you would find is that the expression looks something like this. You see what's going on surface J is now connected to what's going on surface I. And how is it connected? It's connected through these matrix elements down here. These matrix elements down here are called derivative couplings, and these are called the first derivative couplings. Down here, they're called the second derivative couplings. And if you look and you see what's going on, look at this. This is the derivative of the wave packet on I. This is telling you that when you move on surface I, it's measuring your speed moving on surface I. Your speed moving on surface I is connected to a possible transition from surface I to surface J. That's exactly what I was trying to say before. That if you move on one surface, you can actually hop to another surface depending on how fast you're going. If you're moving very slowly, you stay on one surface. But if you're moving very quickly, you can jump to another surface, just like we talked about in the water-water situation. So all of that information about electron transfer is hiding in these so-called derivative couplings. These derivative couplings are where all the magic is. What really matters is how these adiabatic states depend on nuclear position. And when you figure that out, you can figure out how you actually couple one surface to another, and then therefore how electron transfer happens. Now, usually these terms are not big. If you go to any textbook, any textbook you can think of in chemistry, the first approximation is that they're always zero. And in solids, they almost always are zero. And again, most people ignore them entirely. However, people like David Yarkoni or our friend who just passed away, they spent their lifetime working on these derivative couplings, and it's known that in fact they can diverge. In fact, we know exactly when they're big. How do we know this? Well, it's a very simple argument. Imagine you were taking your electronic Hamiltonian and diagonalizing it. Then if you had two states with different energies, say states 1 and 2, then this expectation value, this matrix element must be 0 because the Hamiltonian diagonalizes psi 1 and psi 2, which means if you take the derivative of it, take the derivative of psi 1 plus the derivative of h plus the derivative of psi 2, that whole thing also must equal 0, and then of course h on psi 2 gives you E2. And h on psi 1 gives you E1 if you're looking at these electronic states. So you have this equation. And if you also have the equation that d by dr, you also have the equation that psi 1 with psi 2, the overlap of these two eigenfunctions is 0, then the derivative is also 0. You get this expression, which tells you that these two matrix elements are equal and opposite. And if you plug that in back up here, you then convince yourself that this derivative coupling actually looks like this, which is called the Hellman-Feynman expression, psi 1 dhdr psi 2 over the energy gap. In other words, the derivative couplings are big when the energy gap is small. So if we go back to the lithium fluoride case, it tells you that when you go to this region in here, where the two characters of the electronic states change and the two energies come close together, that's where the derivative couplings are large, and that's where the system decides whether an electron transfer occurs or doesn't occur. This is all the common lore of non-adiabatic chemistry. And so here's an example of what the derivative coupling looks like for lithium fluoride. It's peaked around 7 angstroms, right in here, that are in the avoided crossing. So these are my conclusions. All of our intuition, for the most part, in quantum chemistry and in quantum dynamics is based on adiabatic electronic states. Electronic states are coupled. These electronic states are coupled by derivative couplings. Derivative couplings are big near curve crossings. And the theory of electron transfer is always tied to the notion of curve crossings of adiabatic states. This goes back to the work of Marcus and Jortner and Hush. Um, um, and nuclear motion is what drives electron transfer. The questions that I'll be asking in my talk are these derivative couplings important only near curve crossings? And I'll argue that no, this has been missing. And is the adiabatic picture the right one to begin with? And I'll argue that no. And that will be what goes on in my talk. And these questions are the essential, motivation for going forward. I hope you enjoyed this. Thank you.